Hello everyone. In this video, I'm going to talk about error in Maclaurin and Taylor series. So in the previous videos, we have learned how to figure out the first few terms of Maclaurin series or Taylor series for a particular function. But if we truncate a Maclaurin or Taylor series after a certain number of terms, then what is the error that we incur? Alright, so we know that Maclaurin series is written as an infinite series. Fx is equal to f0 plus f prime 0 x plus f double prime 0 x square over 2 factorial and so on. But if we want to write this infinite series in terms of a finite series, so it looks like this. So you write the first few terms. So let's say we write n terms, and then after that we write plus Rn x. And what is this Rn x? So that specifies the remainder form of the series. So basically, so the terms like n plus 1th term, n plus 2th term, and so on up to infinity. So all other terms we replace by Rnx, where Rnx is given by the formula Rnx is equal to nth derivative of function around some unknown z, x raised to power n plus 1 over n plus 1 factorial. So we notice that, so this formula is just, it looks like the next term in the series, except the derivative is to be evaluated at some unknown location. So exact same form as any term of the series. The only difference is that the derivative is evaluated at some unknown location z. So now when we truncate the series, this can be considered to be the error if we truncate the series. The only problem is that Rn depends on z and we don't know z. So the answer is to simply choose z to give the biggest possible Rnx in absolute value, and then we have an upper bound on the error. I hope that makes sense. So because we don't know what is that, so what we can do is we can figure out the maximum absolute value of this function, which would be the upper bound of our error. Thus we can write our series as fx is equal to f0 plus f prime 0 plus so on, so nth term, plus minus en, so which is our maximum error possible due to cutting off the series after x raised to power n. So this error is given by, so it's just written in the formula form here. So maximum absolute value of Rn over the interval 0 to x. So we get a similar error formula for Taylor series, as we know that Taylor series is expanded around x equals to a. So the maximum error after cutting off the series after x minus a raised to power n term, so that error is given by this formula. So the only difference is we look at the maximum value of this Rn term on the interval a to x. Let's do a few examples to figure out the errors. So find a bound on the error made when we use the first three terms of Maclaurin series of the function e raised to power x to approximate e raised to power 0.5. So bound means we want to figure out the biggest possible. So first we start by figuring out the Maclaurin series for our e raised to power x function, and we know that it is given by these terms in the series and so on. Since for the function e raised to power x, so first derivative, second derivative, so all the derivatives are equals to nth derivative, so all the derivatives are equal to e raised to power x, and if you evaluate these at 0, so e raised to power 0 means just 1. So let's plug in these values here. So our Maclaurin series for e raised to power x is 1 plus 1 times x plus x square over 2 factorial. And since I'm only writing first three terms, so if I just want to use first three terms, so after my third term, I'm going to write plus minus some error. And since I am stopping at x square term, so I use e to x. Let me remind you. So when we were stopping after nth term, so we were writing en x when we discussed this concept. So right here, so when you stop at x raised to power nth term, so error is written as en x. So if you stop at x square term, so then you're gonna write e to x. And now we need to approximate e raised to power 0.5. So let's put x is equal to 0.5. So at x equals to 0.5, we get e raised to power 0.5 is equal to 1 plus 0.5 plus 0.5 square over 2 factorial plus minus e to 0.5. So now our goal is to find what is this value. So what is E2 at 0.5? So we start with our error formula. And since we need E2 at 0.5, so we put n equals to 2 and x equals to 0.5. And also third derivative of our function, exponential function, is e raised to power x, and since we want it at unknown location z, so we write e raised to power z. So after plugging in all the values, so 0.5 raised to power 3 over 3 factorial comes out, and we find the maximum value of e raised to power z over the interval 0 to 0.5. And since it's an increasing function, so the maximum value occurs at 0.5. So in the end, we get approximately 0.034348359 as our bound on error. So thus, in case of e raised to power 0.5, if we use only first three terms, so we get 1.625. And since we are only using three terms, so maximum error that we can have is 0.03 as compared to the actual value. So it means it belongs to this interval 1.625. So we subtract the e2x for our lower limit and we add it for our upper limit. So 0.034348359. Alright, so it means e raised to power 0.5 belongs 1.590652. So the actual value should be in this interval. So we can get an idea about the exact value, like we can estimate like what interval the exact value gonna lie in just by looking at first few terms. So you can actually check it. So if you use the calculator, so your calculator shows that e raised to power 0.5 is 1.648721271, and error, if we use the first three terms, so that error is going to be the difference between the value that we calculated from the first three terms minus the actual value, the calculator value. So this is our calculator value and this is our value with three terms. So what is the error? So error in this case we get is 0.023721271. So it means we can figure out, like if you're looking for a particular accuracy, like maybe you want to accurate up to 3 decimal places, so you can increase the number of terms of the series based on how much accuracy you want. So in this case, we just use the first three terms and we saw that the error that we get is this one, 0.023721. So in the next example, I'll show you how do we decide on the number of terms for a particular accuracy. So in this example, we need to figure out how many terms of Taylor series for e raised to power x expanded about a is equal to 1 must be used to calculate e raised to power 1.1 accurate within. So this is our accuracy. So we know that the error in Taylor series after x raised to power n term is given by e n x equals to, so maximum value over the interval a to x of n's derivative at z x minus a raised to power n plus 1 over n plus 1 factorial. Now at a equals to 1 and x equals to 1.1, so that is given in our problem. So this is our e raised to power x, right? So we get, so for this problem we need to figure out, so maximum value over the interval 1 to 1.1. So nth derivative at z, so 1.1 minus 1 raised to power n plus 1 over n plus 1 factorial. All right, so we get, and also I can plug in my function here. So my function is, so since my function is e raised to power x, and we also know that any derivative, so nth derivative of this would be also e raised to power x. So here instead of writing nth derivative at z, so I can simply write e raised to power z. So in the next step, what we can do is, so we can bring our constants outside. So 1.1 minus 1 is 0.1. So raised to power n plus 1 over, so n plus 1 factorial. And here the variable is z. So maximum value of e raised to power z over the interval 1 to 1.1. Since exponential function e raised to power x is an increasing function, so it means the maximum value is going to happen at the upper bound of this interval, so it's going to happen at e raised to power 1.1. All right, so now what we got here is that our error should be, so error at 1.1 is equal to e raised to power 1.1, 0.1 raised to power n plus 1 over n plus 1 factorial. So that is our error. But what we want is, we want the error to be less than equals to 10 raised to power negative 6. So that's the accuracy we want. So it means e raised to power 1.1, 0.1 raised to power n plus 1 over n plus 1 factorial less than equals to 10 raised to power negative 6. So in order to find such n, so what we can do is, we need to plug in some n values and see after what x raised to power n term we get error less than 10 raised to power negative 6. So let's try some values of n. So if I use n equals to 2, so e2 1.1, so that is equals to 1.1, 0.1 raised to power 2 plus 1 is 3, so over 3 factorial. So this is approximately 5.01 times 10 raised to power negative 4. So this is greater than 10 raised to power negative 6. So this doesn't work. Again, you can try e equals to 3. So n equals to 3, sorry. So if you put n equals to 3, so you get e raised to power 1.1, 0.1 raised to power 4 over 4 factorial. So that is approximately 1.25 times 10 raised to power negative 5. Again, this value is greater than 10 raised to power negative 6. So let's try n equals to 4. So E4 1.1. So when we calculate this, so we get 2.50 times 10 raised to power negative 7. And clearly, this is less than 10 raised to power negative 6. So we need to stop. So stop here. So stop after the term involving, so what power of x? So n is 4, so it means the term involving, and since this is a Taylor series around 1, so x minus 1 raised to power 4. So stop after this term in order to get the accuracy of 10 raised to power negative 6. So now let's try to write the Taylor series around a equals to 1 for the function e raised to power x. So that would be a naught plus a1 x minus 1 a2 x minus 1 square over 2 factorial a3 x minus 1 square over cube over 3 factorial. And since we want up to the terms when we involve 1 x minus 1 raised to power 4 over 4 factorial, so we'll stop here. A naught is just the value of the function at a, so that means the value of function at 1, so which means e raised to power 1, which is just e. And similarly, a1 is the first derivative at a, so e raised to power x at 1, so it means that is again e. And similarly, we have a2, so we know that all the higher order derivatives and a3, so all the higher order derivatives is gonna be the same. So find the value at 1, so e raised to power 1, e raised to power 1, and a4 is also e raised to power 1. So plugging in the value of all the derivatives, we get e raised to power x is equal to, so it's just first few terms, so we get e raised to power 1 plus e raised to power e times x minus 1 plus e times x minus 1 square over 2 factorial plus e times x minus 1 cube over 3 factorial plus e times x minus 1 raised to power 4 over 4 factorial. So e can be taken as a common factor out. So we get, so this series is 1 plus x minus 1 plus x minus 1 square over 2 factorial plus x minus 1 cube over 3 factorial plus x minus 1 raised to power 4 over 4 factorial. So how many terms did we calculate? 1, 2, 3, 4, 5. So we need 5 terms of the Taylor series to get an accuracy of 10 raised to power negative 6. So we stop after n equals to 4. So that means we need the first 5 terms. I hope that makes sense. So let's just try one more problem. So in one of the previous examples, like in the previous video, not this video, we found that the first 3 non-zero terms of Maclaurin series for sin x were this. Find a bound of error in computing sine 95 degrees using just first 3 terms. So if you recall, we have done in the previous video, we figured out for sine of, so 95 degrees, so that means 1.6581 radians. So that's what we did in one of the previous examples. So now we're going to figure out what is the bound on the error in computing this value if we use just 3 terms of Maclaurin series for sin x. So if we look at this series, so first 3 non-zero terms, so what we will think in our mind that we should calculate e raised e5. So should we calculate e5? So if we look at the first 3 terms of this sine series, so we stop at x raised to power 5 over 5 factorial. So in our mind, we will think, oh, we should calculate e5. But let's take a look and think a little bit deeper. So we know that in sine series, all the even powers of x vanish. So it means the term, the x raised to power 6 term is 0. So we really want to know the error after x raised to power 6 term. And what was our error formula? So this is our error formula. So if we plug in n equal to 6 in this one, so we get error after x raised to power 6 term is maximum of z belongs to 0 to x. So seventh derivative at some unknown z. So x raised to power 7 over 7 factorial. And now, so let's put x equals to 1.6581 radians. So that would be equal to, so let's plug in the value. So maximum z belongs to 0 to x. Seventh derivative of our sine function. So 1.6581 raised to power 7 over 7 factorial. So this problem, one way is like you don't really need to figure out the seventh derivative, because we know that whether it's a sine function or cosine function, because we know that when we take the derivative again and again of sine function, so either you end up with sine or cosine in the end. And if you're looking for the bound of that function, so the maximum value can be only 1. So you can simply write 1 times 1.658 raised to the power 7 over 7 factorial. But if you still have doubts, you can always figure out the seventh derivative of sine x. So maximum, so in this case, let's take out 1.6581 raised to the power 7 over 7 factorial out, and we need to find the maximum value over the interval 0, 1.6581 of our function negative cosine z. And I don't really need to plug in the values, so that maximum value would be 1, because cos function is bounded by 1. Sorry, I should have changed my x value here as well. So let's change it here now. So we found that the bound on the error is 0.00683. So let's now try to use our first three non-zero terms of sine series and see what we get. So when we plug in the value 1.658, so we get approximately 1.658 minus 1.658 cube over 3 factorial plus 1.658 raised to the power 5 over 5 factorial plus minus E6x. So E6 at 1.658 is 0.00683. So from here we get, so from the first three non-zero terms we get 1.00278. So plus minus 0.00683. So this is the error that we get after using first three non-zero terms. So it means the value of sine of 1.658 belongs to, so if you plug in the 1.00278 minus this value, so you get 0.99595, and if we add it, so I'm going to get something like 1.00961, so which is not really a good thing, because we know that sine cannot go beyond 1. So this is again a upper bound, but 1 is the maximum. So this should be 1, because sine x, so absolute value is less than equals to 1. So if you look at the calculator, so what does calculator shows? So calculator shows you that the actual value is, so sine of 1.658 is approximately 0.9962. So it means what we got here is overestimation. So we need more terms if we really want a good accuracy. So we have this much error in our value. All right, so I'm going to quickly show you one more example in which you will figure out how many terms should we consider to get desired accuracy. So in the previous example, how many terms in the Maclaurin series should we use in order to get sine 95 degrees or sine 1.658 radians within 10 raised to power negative 6? So this much accuracy. So it means we want to solve the error formula. So E n at the point 1.658, and we want this error to be less than 10 raised to power negative 6. So we're going to solve for that n. All right, so I'm going to go ahead and write my formula. So we figured out in the previous example. So this is given by maximum of z belongs to 0, 1.658, nth derivative at z, 1.658 raised to power n plus 1 over n plus 1 factorial. And we know that, so the nth derivative is going to be either sine or cosine, and the maximum value of that is 1. So in the next step, I just write en 1.658. So that should be less than equals to 1.658 raised to power n plus 1 over n plus 1 factorial. And we're going to solve this for n. So let's try some n values. So in the previous example, we already tried up to like E6, right? So, and we got a big error. So let's try some bigger values for n. So I'm gonna try n equals to 9. So E9, 1.658. So that gives me 1.658 raised to power 10 over 10 factorial. So in this one, so which is approximately 43.3 times 10 raised to power negative 6. So which is greater than 10 raised to power negative 6. But we want error less than 10 raised to power negative 6. So let's try n equals to 10. So when I try n equals to 10, I get approximately 6.5 times 10 raised to power negative 6. Again, this is greater than 10 raised to power negative 6. Okay, so what about 11? So if you try n equals to 11, and you will get approximately 0.9 times 10 raised to power negative 6, and which clearly is less than 10 raised to power negative 6. So here we stop. So it means we should stop after the term x raised to power 11 term. So we need to stop. We need to stop at the x raised to power 11 term. So it means what kind of series we use. So we should use these terms. So sine x is x minus x cube over 3 factorial plus x5 over 5 factorial minus x7 over 7 factorial plus x8 over, sorry, x9 over 9 factorial, and finally x11 over 11 factorial. So if you want the accuracy, or in other terms, if you want 10 raised to power negative 6 accuracy, or you can just write this in summation form. So negative 1 raised to power n, and then x raised to power, so all odd power, so all odd number is written in the form 2n plus 1 over 2n plus 1 factorial, where n goes from 0 to 5. So it will give you these 6 non-zero terms of sine series that you need in order to get 10 raised to power negative 6 accuracy in your result. I hope that makes sense. So whenever we truncate any Maclaurin or Taylor series, we can always find the error that we are making when we are only considering few terms of the series. If you like this video, please hit the like button and subscribe to my channel. See you next time. Bye for now.